speech will be presented by Dr. Santanu Day. He is the assistant professor in the Mechanical Engineering IIT Kanpur. He got the Bachelor of Engineering from North Bengal University in 2002 and MTech from IIT Kanpur in 2004, both in Mechanical Engineering, and received the PhD in Aerospace Engineering from Indian Institute of Science, Bangalore in 2012. And before joining IIT Kanpur, he served 2 years at the Michigan Technological University as the postdoctoral research associate, and 1 year at the Institute of Combustion Technology (ITV), University of Stuttgart. He also worked as the scientist at the Liquid Propulsion System Center, Indian Space Research Organization between years 2004 and 2005, and his primary area of research is.
So welcome to the talk, and I thank you for the nice introduction. During the last day and today, we have heard applications related to locomotives, and then there are concerns about the pollutant reductions and all these things. Also, the combustion efficiency, increase in combustion efficiency. So the combustion efficiency is another key aspect of this. So I'm going to talk about a fundamental study using that is basically the modeling of combustion and that can be applied to any combustion chamber, right? So the talk goes like that: the simulations of turbulent non-premixed flames using stochastic multiple mapping conditioning approach. So the genesis of the work is that I started this work during my stay at Stuttgart, and there I partly carried out this work, and now I am continuing this work with my PhD student. So I am going to talk about the MMC method, and then I will present some of the results. So the outline of the talk is here. So I just quickly go through this. So introductions. So the motivation is that the accurate descriptions of the coupling between the reaction and the molecular mixing. These are the two key elements for success of any turbulent combustion models. Okay. So as you all know that the chemical source term is highly nonlinear. Okay. And there is an inherent difficulties in modeling that nonlinear chemical source terms. So we cannot directly calculate the mean chemical source term using the mean scalar and the mean temperature, right? So therefore we need to resort to some of the modeling approaches. So in past studies it has been iterated that the reaction rates are strongly related to the scalar dissipation. Also the dissipation appears as an unclosed term in most of the turbulent combustion models. So here are some lists of the different turbulent combustion models that could be applied to non-premixed and the premixed combustions. So there are plenty of models that is available for the non-premixed combustion, like the first and equilibrium chemistry model, and AD dissipation concept, and the flamelet model, conditional moment closure method. Similarly, in the premixed combustion, there are BML model, level set approach, flame surface density approach, and PDF approach. The PDF approach can be used for both of these regimes, so non-premixed and the premixed. So it offers an inherent advantage that helps it to apply for any kind of flame. And on this track, actually, the multiple mapping conditioning approach is quite new concept, and that has been emerged in the last decade itself. So that actually tries to derive some of the advantage of the conditional moment closure method and then the PDF approach. So I am going to talk about this MMC method in this talk. So let us know what is the CMC approach. So in the CMC approach, what we do, we try to compute the conditional means. So in any turbulent flow, if you tries to record the different species or any scalars, for example temperature or species with time, then you will get a signal like this. And then if you can extract this conditional average based on a certain quantity, for example the red dots that is there, that represents that the condition when the mixture fraction is a certain value. So mixture fraction is eta there. So if you can average all these red dots, then it will give you the conditional average. So in conditional moment closure approach, we try to calculate the conditional moments by solving some transport equations. And here is the transport equation. I am not going deep into this. So what we have the temporal term, and then the advection term and the diffusion terms like that. But the last two terms are quite crucial. So one of them is the diffusion in the conserved scalar space, and another is the conditional source term. So in the diffusion in conserved scalar space, there is a term like scalar distribution rate term, and that is again a problem. There is a problem in modeling. So there are some empirical relations or the studies with DNS or the experimental data for that conditional scalar distribution rate model. So here are some of the closures of the conditional moment closure method. I'm going to skip this. And on the other side, the PDE method that has been over last 2-3 decades, it has been emerged as a great tool for the simulations of the turbulent combustion. So here actually we try to describe the evolution of the joint PDF following that equation, and then we can also solve this equation within a Lagrangian framework. And then Lagrangian framework, we solve the transport in the physical space and also the transport in the compositional space. Okay. So there are several terms like the diffusivity denoted as dt, and then there are chemical source term omega I, and then the mixing operator Si. So these terms needs to be modeled. So the diffusivity can be modeled from the turbulence model. If you are following the K epsilon model, then you can get a closure of dt. Similarly, the mixing model, there are several of mixing models available for the PDE approach, like the IEM model, Curls model. So those can be used. Now let us come to the stochastic MMC approach. So MMC method could be both deterministic as well as stochastic. So it is basically a logical combination between the probability density function and the conditional moment closure approach. So it tries to derive the advantages from both. So as we know that the PDF method is quite expensive if you want to apply for a DL system, whereas the CMC method is little bit less expensive, but it has been found that CMC method cannot produce certain flow features, complex flow features such as the extinction and the reignition. So there have been some problems associated with the CMC method, whereas the PDF method is advantageous since it can capture those phenomena, but at a very high computational cost. So the MMC method tries to address that problem, and it utilizes lesser computing time compared to the PDF method. I am going to demonstrate that through some results. So in MMC method, what we do, the turbulent fluctuations are modeled into major, are actually basically classified into major and minor groups. Okay, and the fluctuations of major scalars are not restricted, and the fluctuations of minor species are correlated to the major species. And multiple mapping conditioning, it actually started from the mapping closure method of Pope and the Chen et al. So in mapping functions, we describe a mapping function and we try to evolve the mapping function over time. Okay. So the major mixing time scale controls the turbulent mixing of the characteristics quantity via the modeling of a mapping function, whereas the minor time scale basically controls the fluctuations of scalar relative to the major fluctuations. So the equations for the MMC approach are basically similar to that of the Lagrangian PDF method. In addition to the transport in the physical space and the composition space, there is another extra term, that is transport in the reference space, that is d xi. So here actually the star refers to the stochastic particles. Okay. So we are basically trying to solve several particles throughout the domain, and then we are averaging it to recover the unconditional quantities. Okay. So in like PDF method, there are 3 sets of equations that needs to be solved, and of course there is a mixing model that we need. So here actually we use the modified Karl's model. So that has been derived from the PDF, the modified Karl method that is applicable to PDF method. So we have adapted that for our purpose. So what is important here actually in the mixing model, we are basically mixing two particles with one another at certain rates. So that rate is coming from the turbulence quantity like the tau phi, and also there is a minimum, the tau minimum, that actually governs the minor fluctuations. So tau min is basically related to the turbulent time scale tau phi using a constant C min. So that C min is again another constant that we need to be tuned in to get a reasonable match. So the recent DNS results has recent DNS results for a homogeneous isotropic turbulence has proposed that C min value to be used as 0.5. So we have done several studies with different constant and so that we can get a very good estimate of different quantities. So now I am going to the results part. So first I will start with the pilot stabilized flames. So here actually we have simulated the Sandia series, so D, E and F. So these flames are basically stabilized by the hot pilot stream, and on the side there is a ambient air, and then the central there is a jet. So jet composition is 25% of methane and 75% of air, and that gives us a stoichiometric condition of 0.351. So we have simulated 3 cases with 3 different Reynolds number. So the flame D is actually a very stable flame, and if you increase the Reynolds number, we are going towards the extinction. Okay. So the flame F is actually gives some local extinction and reignition. So our purpose is to apply the stochastic MMC method to capture some of these phenomena. Okay, so here is a sensitivity study with the different value of the mixing constant. So we have here used 3 different mixing constant, so 0.1, 0.5 and 1, and if you see that if I increase the mixing constant, the particles are actually scattered a lot. Okay. So if you see that 0.1 gives a very less scatter, and if you go increase that, it gives more and more scatter. So similarly in the second row we have the mixture fraction over reference space. Okay. So again you can see a higher amount of scatter if you increase the mixing, and that is actually obvious from our mixing model. Okay, so here we compared the temperature scatter plots with the experimental results as well as the previous PDF results, and we have used 3 different constants here. So C min 0.25, 0.35 and 0.5, and what we find that if I increase the mixing constant like 0.5, we get a wider range of the scatter, and if I reduce that, we get a very less amount of scatter, and if you compare it with the experiment, then I think the 0.5 appears to be, or 0.35, both of them are in very close to the experimental as well as the PDF results. Similarly, now I have plotted the unconditional mixture fraction. So what we have done, so the radial profiles of the unconditional mixture fraction is plotted at different axial locations. Also I have plotted the RMS value of the mixture fraction. So as you know, the mixture fraction is a very important quantity, and that will give us some idea about the film structure. So, and if you compare it with the experimental results, then we have obtained a very good match with the MMC curl method, and I have also plotted the PDF curl method. At places there is some over and under predictions from the PDF method, but overall actually both of them are in reasonable agreement with each other. So here are conditional temperature profiles. So we have extracted the conditional temperatures from our simulations, and both the conditional mean and the conditional RMS of temperature are shown here. So MMC curl gives a better agreement because we have tuned the mixing constant here. So this set of result is obtained using a constant of 0.35. So by tuning the mixing constant, we can actually predict better results. So that is one of the important aspect. Whereas the PDF curl, there is no, the agreement is not that good at some locations. So same thing about the unconditional temperature. So at different axial locations it has been shown, and overall except one location for the RMS and the mean, so at x by d 30 there is some deviations, otherwise it captures, it gives a reasonable good agreement. So we have also done a sensitivity study with the particle numbers. So we have done several of, we have simulated the flame E with the different particle numbers. So 10, that is represented by the blue line, and the 50 by the pink line, and the red, that is the solid lines, red solid line, that is 100 particles. And we see that the RMS of temperature does not change very much if I use 10 and 50. Okay. So overall it gives that with a very less number of particles we can simulate this. In previous numerical studies using PDF, so some of the numerical experiments have been done with a large number of particles. So one of the paper by Cow and Pope, it used several, and the Lindsay and other co-workers, they have used several hundreds of particles per CFD cell. But here actually in MMC we have tried to define two different times of times constant, and thereby we could get a reasonable agreement with a significantly small amount of particles. So in summary, this modified curl method for MMC method has been developed for the pilot stabilized flame, and the computed conditional and unconditional profiles of both mean and RMS of reactive scalars are found to be in overall good agreement. We have carried out the sensitivity study with different mixing constant as well as the particle numbers. So next we have moved to the lifted jet diffusion flames. So here we have used the Cabra burner with methane and air as a fuel, and the central jet. So methane is used as a fuel, and it has been supported by a hot co-flow air. Okay. So some of the conditions for these simulations are listed here, and we have a Reynolds number of the jet of 28,000 corresponding to a velocity of 100 meter. So the co-flow is hot and it is 1350 Kelvin. So here is some flame structure from the numerical simulation. So OH contour is basically shown here. So you can see that the flame is lifted flame, it is not anchored to the burner. So here are some unconditional temperature that we obtained from the simulations and plotted with the experimental measurement, and except the x by d 15, we see that overall the agreement is very good in both in terms of the mean and the RMS. Now here is the conditional temperature, that is plotted the temperature in the mixture fraction space. So we can again find a very good agreement with the experimental results. So this should be conditional mixture fraction and the RMS of mixture fraction. So we again see a very good agreement. Again the center line profiles for different scalars like the temperature, mixture fraction and species mass fractions are plotted here at different axial locations, and the match is reasonably good. So in summary, the predicted lift-off height of the methane air lifted jet diffusion flame appears to be in close proximity with the experimental data, and the computed conditional, although I have not shown that. So actually the lift-off height is around 35, so we have got 36 or something with that. So the computed conditional and unconditional profiles are also found in good agreement with the experimental measurements. So the overall conclusions, so the stochastic MMC method has been applied to two different flames, and we have found that conditional fluctuations are modeled accurately by tuning in the constant C mean. So this gives us the flexibility. I mean, in MMC we can just tune in that constant and try to get a good agreement. So what I have found initially, what we have done, we have used the C mean 0.35 for the pilot stabilized flame, and later the same constant we have used for the another configuration. So it appears that the value of the constant C mean should be in proximity to 0.35 to 0.5 in that region. So if we can use that constant in our simulations, then I think we are going to predict reasonably well. Okay. So we can capture the physical behavior of flames such as extinction and reignition, and this method is computationally cheaper than the conventional PDF method. So overall we have obtained a very good agreement with the experimental results. So I would like to acknowledge my postdoc advisor, Professor Cronenberg from University of Stuttgart, and my co-worker, now she is a faculty at City University of London, Constantina. So this work is initially started with in collaboration with them, and also the Carmen Staub, she is a research scholar at Stuttgart, and currently I am pursuing this with one of the research scholar at IIT Kanpur, so Sanjeev. So he is basically computing the lifted jet division flames. So in future we are trying to implement this MMC method to the premixed flame as well as the stratified flames. So thank you for your attention.
Thank you very much for your very interesting presentation. Any questions or comment from the floor? Yes, please.
Yeah.
Glad that there is something that is more efficient than PDF. I hope.
No, we are still in the initial stage, and I think it is premature to claim that. So we are trying to simulate other flame series for the non-premixed flame, and if it works, yes, yeah.
But I was curious. You mentioned some, I guess, we call them mixing constants.
Yeah.
I presume this is like a free parameter you have that is some kind of empirical constant that appears when you have resolution.
Right. Right.
And so I presume that there is at least one per equation. You have like
No. That is only one constant.
so this is one constant.
Right. So
That's the values. In one case you mentioned 0.1, 0.51, then you said 0.35.
no, we tried to do a sensitivity study with this C-mean, this constant C-mean. So that actually scales models the minor fluctuations in terms of the major fluctuations. So this constant C-mean, if it is 1, then the major and the minor fluctuations are related to each other. If it is 0.5, then we scale it down. And
But you also have the, I guess, free parameter, which is the number of particles per cell, right?
right.
And in this particular case, for example, you have been more able to get down and right?
Right.
Now that again is an arbitrary choice.
So it is basically like I would like to conclude it like a grid independent study. What we do for the for our CFD problem. So there we play with the different grids and then come to a converse solution and then say that okay, that is the converse data. So here actually we can play it around with different particle numbers until we get a particle independent solution.
But I suspect that if I'm looking at the physics, it's not really a number that would be universal because presumably it's related to the variation of the gradients you have. Like if I'm doing a gradient independent study,
Right.
there is some kind of gradient that controls the overall thing, and the grid size eventually has to relate that.
Right.
You were able to get away with 5 or 10 as opposed to some other examples, presumably because your flame at that point or for a crucial region where it happens, the mixing happens, is perhaps less.
Right. So
The other flame might be, like if you take a triple flame,
correct.
you might need a lot more than 10.
Right.
Correct?
Right. Yes, I think that is a valid point. So I think for in our simulations, so I say that it is 10 particle. So that means that I have a range. I have defined the range to be 5 to 15. So if the particle number goes beyond 15, then okay, I take away some particles and bring it down to 10 or 15. If it goes below 5, then I clone some of the particles. I generate some of the particles. So that thing is done in the code. Another thing is that this is more or less steady flame, like the pilot stabilized flame what we have investigated, except some local extinction and reignition. And all these results which I presented is averaged over a significant amount of time. So that probably takes care of the, I mean, when you average it with time, then you'll be able to get a converse solution, in my opinion.
I presume it's non-linear phenomenon.
Mm-hmm.
More particles.
Right.
Your math cost will go up by n square, I presume.
Mm-hmm.
And since it's a random process, I'm presuming that your accuracy is improving by square root of n.
Right.
Does that still hold in this case also?
No.
Like Monte Carlo shows that. That's what happens in Monte Carlo.
Mm-hmm.
Your accuracy would be proportional to
Right.
square root of n and your cost moves n square. Is that
Yeah.
the same?
So I mean, I've not investigated deep into this result. So, but yes, I think I should check that. So in terms of the accuracy, how it is affecting. Right, right. So, right. So it may not be universal. So what I propose that, okay, we can start with some particle number, and then if we increase and if we can see some change in the results, then okay, we have to increase the number of particles. So it is, I have taken it just like a sensitivity study for, I mean, based on the particles. So nothing more than that. I am not, right, right, yeah.
I mean, this is very good work, but I'm just saying that it's more that certain expectations are built when a new model comes.
Right, right.
And the reality then at some stage requires that we have a efficient process.
Right.
So I think it's very important to understand how should I say, the cost of the physics involved.
Mm-hmm. Yes. Yes.
Differently, and so we need to understand, for example, we now know that KF does not work in some situations that we didn't know in 20 years ago, right? I think similarly it's very important that we need to understand there's so much work going in PDF, but there's so much of confusion and nobody really still understands when PDF works and when it is working and when it is not, right? So I think we need to get to the limits, when does it work, what is it called?
Right, right. Okay. Yeah. Thanks for your comment.
Thank you very much for the presentation and very fruitful discussion.